morgon och hjärtligt välkomna. That was my Swedish introduction. You are most welcome and good morning. It is another chilly day now in November, in actually the 1st of December here in Gothenburg. And finally the sky is slowly clearing little by little. We have a cold front coming in. I will take the last bit of mathematics in Roberto Unger and Lee Smolin's book, The Singular Universe. And then I will have time for the promised quantum mechanics of present. It's page 331, last paragraph of the page, and we are presently having 1282. In the history of physics, no example of supposedly pre-natural power of mathematics to lift the veil of nature is more striking than Newton's inverse square law of gravitation, according to which the gravitational force connecting two bodies varies in direct proportion to the product of their inertial masses and in the inverse proportion to the square of the distance between them, while the square of the distance rather than some other less simple and pleasing measure, why the neat and disconcerting symmetry, and why does an inverse square rule apply to a number of physical phenomena other than gravitation? Newton's inverse square law accords with a visual representation that we have independent physical reasons to take as accurate, appealing to conserved lines of force or flux lines. Imagine the gravitational field of the sun to be represented by lines fanning outward from the center of the sun, always in the radial direction. Suppose further the existence of a planet moving in a circular orbit at a distance d from the sun's center. Let us assume that the force felt by the planet is proportional to the density of the field lines at the distance d. The density falls off as 1 through d square. It falls off at this rate because the number of field lines intersecting a sphere of any radius around the sun remains constant. The density, which is the number divided by the area of the sphere, diminishes according to this area, which is d square. Consequently, the force weakens at the measure of 1 through d square. Only if the force falls off according to the rule 1 through distance minus squared will the picture of lines of force that I earlier invoked hold. An instance of the same way of thinking, not directly related to gravity, suggests the generality of the spatial reasons for its wide application. compute the dot product of the force field with the unit normal to the surface and integrate the resulting function over the surface. The result is proportional to the mass of the interior bounded by the surface. This relation recurs no matter how the mass is distributed. The same mathematics works for the electric force with electric charge in the place of mass. It works as well in a number of other contexts for reasons that have to do with a regular and recurrent spatial disposition of natural forces in the established universe. The less we grasp the non-mathematical reasons for the application of mathematics, the more enigmatic and disconcerting the application of mathematics will appear to be. We will be tempted to bow down to mathematics as the custodian of nature's secrets, that the laws of parts of nature are written as mathematical equations, then bewitches us into believing that all the workings of all of nature are foreshadowed in the truths of mathematics. A study of the history of mathematics properly understood can help save us from these illusions. Having departed initially from our direct experience of the world through its extirpation of time and phenomenal particularity, mathematics moves yet farther away from it thanks to overriding influence of internal development. Only its engagement with science qualifies this influence, as science comes to play for mathematics the role that our sensible experience of nature once performed. Nevertheless, by the paradox that characterizes the entire history of mathematics, this removal from the world of the senses only increases the power of mathematics to suggest new ways of thinking about how parts of reality may connect. As a result of the sovereignty of internal development, the relation of mathematics to nature now mediated through science becomes so indirect that whole branches of mathematics may shift or even reverse their use in the mathematical representation of natural reality. For example, algebra, culminating in set theory, was traditionally understood as the mathematical investigation of structure, analysis, beginning in calculus as the methodological instrument for the depiction of change. Yet in the dealings between mathematics and the science of the recent past, this allocation of rules has been largely inverted. Analysis has been married to geometry. As in harmonic analysis, quantum theory has depicted change by linear transformations on Hilbert space. It follows from this interpretation of the history of mathematics that any given mathematical construction will have no assured application to the one real world. The price that mathematics pays for the enhancements of its power through internal development is the loss of any guarantee that its ideas will find application in the study of nature. Some will and some will not. Having fallen short of the world through the exclusion of time and particularity, its ideas will also overshoot the world. They will be both too little and too much to hold a mirror to reality. We shall have to dispense with the hope of a pre-established harmony between nature and mathematics. Consider now the reverse question. Will every part of nature be susceptible to mathematical representation? Once again, the answer is negative. The greater the salience of time and phenomenal particularity, the more changes, and the more richly defined and individuated the natural kinds and their individual embodiments, populating the aspect of the world that we study. The more limited the use of mathematics will be, imagine a spectrum from the domains in which we should expect mathematics to play the largest role to those in which we can expect it to play the smallest. Each place in the spectrum is defined by the marriage of a part of nature to a practice of explanation. This marriage may be dissolved from time to time. The substitution of one explanatory practice for another. In the study of a certain part of nature is likely to result in a displacement on this spectrum. The easiest case for the widest application of mathematics is the tradition of physics that Galileo and Newton began. In particular, this tradition, insofar as it conforms to what in this book we call the Newtonian paradigm, The objects of this science are recurrent phenomena governed by time-reversible laws. The particularity of the explained phenomena is reduced to a minimum. They are a small number of forces operating among entities whose distinctive characteristics are disregarded except with respect to variations of mass, energy, and charges. This science finds a way to deal with change locally that leaves both the observer and the laws governing change safely outside the domain of the phenomena to be explained. Movement along a trajectory under the aegis of timeless laws is then all that is left of time. The stipulated initial conditions defining the configuration space of the phenomena to be explained are deprived of a history. They wait to be promoted from stipulation to explained subject matter in some other application of the same practice. So I end Roberto Mangabeira here at page 334, and I will continue with that. Just going to remove my I will continue this most interesting part of the mathematics, and I can add also I contacted someone I made before, Newcomb Greenleaf, whose video you can also see on YouTube. I will put in a link to him. He's a defender of a sensible mathematics as an alternative to this Platonic realism, constructive mathematics, or even more algorithmic mathematics. The quantum mechanics of the present, an article in only 12 pages. I will read the abstract anyways. It could be a help to this rather unapproachable subject. This is also, I have to add, extremely recent. It's just from the year before. Abstract. We propose a reformulation of quantum mechanics in which the distinction between definite and indefinite becomes the fundamental primitive. Inspired by suggestions of Heisenberg, Schrodinger and Dyson, that the past cannot be described in terms of wave functions and operators, so that the uncertainty principle does not apply to past events. We propose that the distinction between past, present and future is derivative of the fundamental distinction between indefinite and definite. We then outline a novel form of presentism based on a phenomonology of events. Where an event is defined as an instance of transition between indefinite and definite. Neither the past nor the future fully exists but for different reasons. We finally suggest reformulating physics in terms of a new class of time coordinates in which the present time of future event measures a countdown to the present moment in which that event will happen. Introduction. The idea we will discuss here has arisen from time to time since the invention of quantum mechanics. Here are the earliest quotes we found so far. This formulation makes it clear that the uncertainty relation does not refer to the past. Werner Heisenberg. For eternally and always there is only now, one and the same now. The present is the only thing that has no end. Schrodinger. I deduce two general conclusions from these thought experiments. First, statements about the past cannot in general be made in quantum mechanical language. We can describe a uranium nucleus by a wave function including an outgoing alpha particle wave, which determines the probability that the nucleus will decay tomorrow. But we cannot describe by means of a wave function the statement, this nucleus decayed yesterday at 9 a.m. Greenwich time. As a general rule, knowledge about the past can only be expressed in classical terms. My second general conclusion is that the role of the observer in quantum mechanics is solely to make the distinction between past and future. The role of the observer is not to cause an abrupt reduction of the wave packet with the state of the system jumping discontinuously at the instant it is observed. The picture of the observer interrupting the course of natural events is unnecessary and misleading. What really happens is that the quantum mechanical description of an event ceases to be meaningful as the observer changes the point of reference from before the event to after it. We do not need a human observer to make quantum mechanics work. All we need is a point of reference to separate past from future, to separate what has happened from what may happen, to separate facts from probabilities. Freeman Dyson. There seemed to be something correct in these statements, but they also leave us puzzled. This view seems to treat the future, present, and past differently from each other, but it is also not presentism, which posits that the future and past don't exist. Only the present is real and exists. For if the past is described by classical mechanics, certainly it may exist, and if the future is describable by the quantum wave function, certainly then it represents something that may come to exist in the present. This seems to be true whichever interpretation of quantum mechanics you espouse. There is a view which we may call block presentism, according to which past events, present events, and future events all exist at all times, but their status changes. It seems as if future, present, and past are just labels that can be pinned on otherwise timeless events, which has no effect on their other properties. Then there are hybrid formulations, such as the growing block universe, according to which the past and present are real, but the future is not. But in what sense does the past exist if there is no way for us to alter it? At least not if one is also aspiring to be a relationalist, for whom anything that exists does so as a part of an evolving network of relations and interactions. Taking the passage of time seriously must be more than to draw a thin green line on the block universe to show which slice is presently now. We find the following analogy helpful. Perhaps an observer in the present moment feels no passage of time, the same way a free falling observer feels no gravity. So we began wondering if we could transform ourselves into the rest frame of a present moment observer who would see themselves always at the origin of the time coordinate. From neuroscience, we know that it is possible that with respect to the universe's time, we live in the past and there is no present. There's only the past and the future. It is also possible to define the present as the moment our consciousness becomes aware of the past. This paper is then an attempt to invent a setting within which these thoughts of Heisenberg, Schrodinger and Dyson may make sense. Constructions of space and time. Einstein taught us that our representations of events far from observers are constructions, that is, hypotheses as to distant parts of the world. Quote lost. We tiny, local observers become aware of distant events only from the light, gravitational radiation, and other radiation they send us. We may also prove the universe by sending out light signals and watching for their return as in radar. The times that signals arrive, leave us, or return back can be labeled by readings of a clock. By that we mean physical clock, local to us and weakly coupled, so we read it without destroying it. And that's it. From that meager data alone, we construct a map of the universe into which we fit our knowledge of its history. This philosophy is also extended to our description of the microscopic world as it is seen clearly of operational formulations of quantum theory in which the complexities of the atomic world are broken down into the 3 stages of preparation, evolution, and observations. These stages can also be seen as instances of probing and receiving light signals, at times recorded on a laboratory clock. In this paper, we ask what happens to these constructions when we consider time from a different point of view. We suppose to make a construction of the world that, rather than employing the usual distinction between past, present, and future, is based on a single fundamental and objective distinction, namely the indefinite and the definite. To make this distinction absolute, we need to fix a basis, or what amounts to the same thing. Choose a configuration space, then a state is definite if it has a definite value of the corresponding observable. Otherwise, it is a superposition of 2 or more eigenstates, and we say it is an indefinite state. We regard this as a good thing, even if it breaks the symmetry of Hilbert space. we will argue elsewhere that the distinctions philosophers take to hold between past, present, and future can be reduced to and explained by the distinction between definite and indefinite. On the other hand, in quantum theory, the distinction between indefinite and indefinite appears to underline the distinction between amplitude and probability. We can say that when we observe something, we do so as spectators to the transition between indefinite and definite. In this way, we aspire to construct a compact view of the world compatible with quantum theory and its relativity. 3. A phenomenology of present events. Chasing down the thoughts of Heisenberg, Schrodinger and Dyson leads us to what we might call a phenomenology of time. This can be considered an interpretation of quantum theory, or else a substitute for one. It is a phenomenology in the sense that it organizes how time appears to pervade our experience of the world. We next state the central points of this phenomenology. The definite and the indefinite. Everything that is real is so in the present moment, which is one of a succession of moments. This is a phenomenology of present events. Nothing else exists, or persists. Things only happen. What we mean by becoming or to happen is for something indefinite to become definite. This is what we call an event. Events are real. What becomes definite at any event is not arbitrary. Events happen for a reason, which comes from causally prior events. Events exist for a definite duration and then give rise to subsequent events which make up subsequent present moments. This is how a world based only on the distinction between the indefinite and the definite may define also a causal structure. The quantities that become definite at any event are its endowments, which are passed to each from preceding events and become definite on reception. These endowments include energy and momentum. Each event is brought to happen by the passage of endowments from their immediate predecessors to them. These instances of passing on define the causal relations which are definite. only the becoming, the transition from indefinite to definite is real. To exist is to trace a transitory event. And these transitions are what we call the now, the present. One might try to keep the past as real, with the present as the future-oriented boundary of space-time. But this would be highly wasteful, given that the past cannot have any further influence on the present. A set of events may be co-present, making up the same present moment. A present moment may be thick, that is, contain or overlap with pairs of events that are causally related. The direction from indefinite to definite gives the universe an arrow of time. The quantities that become definite at an event are called the view of the event. The views are real. Once an event that was indefinite becomes definite, it cannot immediately reverse and become indefinite again. Once an event happens, it cannot be made to unhappen. The past. I think a cup of coffee could be good with the past. Not slurp. The past. Events have no past. The influence of the past is already present in the present. We can change neither the past nor the future, but for different reasons. We cannot change the past because it has already become definite, and our only power is to influence what events which yesterday were indefinite become definite, and in some cases what choices were made. That is, that we can only act in the present to influence the process by which the formerly indefinite becomes definite. We can only change the present, and this consists at best of resolving the indefiniteness with which the future confronts us. Traces of these causal partial orders partly constrain the initial conditions for the becoming of the new event. In some cases, these are captured in patterns within a single present moment. To become partial and incomplete records of the past. These give evidence that there may have been previous present moments. In some cases, these records may be detailed enough to allow us to construct a hypothetical science of the dynamics of past moments. We can check records of experiments that were carried out in prior present moments with theoretical predictions derived in our present moment. This is ultimately an exercise in reconstitutional fiction. The future does not yet exist. The future will consist of events at which present indefinites will turn into definites. The future is underdetermined, but we can imagine various paths it might evolve from our present moment and make bets, or what is the same, assign probabilities to them. The indefinite is also called the future. This is because, being indefinite, it can at any time become definite. In an event which is definite and real, if it does, it may influence the present moments to come. The quantum state is nothing but an expression of what we can best forecast or bet about the future, taking fully account both what is indefinite and definite at this present moment. Present moments exist for a finite duration and give rise to successor present moment. But when they do, that previous present moment no longer exists, and the next present moment is made up of novel events. We can call events that we speculate may follow the present events possible future events, but they are not part of reality. because reality is limited to the present moment. We can speak of possible future moments so long as we remember that they are not real. They are speculations about what may become real later. The future is the name we give to speculation as to which events will happen later in reality, which of course means that there are speculations about how indefinites will turn definite in future present moments. The world recreates itself in every moment as indefinites flash into momentary definites, after which they are nothing. Everything we see around us exists or did just exist, but was gone in the blink of an eye. Causality without determinism. The world is causal. All events have causes, and all are causes of other events. The world is generally not deterministic. Pure quantum theory is deterministic in that the evolution of the wave function, the Schrodinger equation, is deterministic. If you input a definite initial state, it will output a definite finite state. That is, it is the indefinite that evolves deterministically. The transition from indefinite to definite is non-deterministic and only given by a stochastic rule. This is how it must be if Leibniz's principle of the identity of the indiscernibles is to be satisfied. For if all the inputs into an event are identical, the outputs must be diverse and not predicted. How much diversity? Enough that each event is uniquely distinguishable. Time's activity is in creating each new event by repeatedly bringing an indefinite to an unpredictable but definite state. So quantum dynamics is perfectly paradoxical. The indefinite evolves deterministically, while the definite becomes so non-deterministically, but causally. Four, the quantum mechanics of definite and indefinite. We have presented a radically different ontology of time than is usually used in physics, which is compared to the block universe picture much sparser. We eliminate both past and future from the description of reality and keep only an ever-changing band of present events. The past is represented in the present in records. Fossils and the like. These give us reason to believe that there were previous moments, but there is no reason to believe those moments still coexist with us. What would that add? What holds up the old house where we sit comfortably writing is not the weight or any aspect of the past, but literally its continual recreation, moment to moment. The future does not exist presently, as indeed it can have no causal effect on us. Saying that the future does not now exist is not saying that anything is possible. The point of having laws of physics is that they restrict what can happen in the future. The present evidence for laws comes from the past by comparison of records of past completed observations and experiments and past predictions for the results of those experiments. Using this knowledge, we can distinguish future evolutions that are possible from those that are not. This does not mean that we give them different ontological status. Very important. Now, the most important question we have to answer is whether the change of ontology we are suggesting implies we must alter the practice of quantum mechanics. This is a slightly subtle question because the different formulations of quantum mechanics do disagree with each other when it comes to the treatment of macroscopic quantum superpositions. The first thing to say is that ours is an event ontology. We do not posit that the world is composed of states. And we mention them only to specify certain ensembles. So if we haven't checked the life of the cat for a few seconds which will be an event when we do so. It is not useful to imagine that there is a cat state. Let us look again at the quotes from Heisenberg and Dyson. We believe it is clear that what Dyson has in mind is a revision of the Copenhagen formulation in which there remains the two complementary realms, quantum and classical. But the boundary between them is moved from microscopic versus microscopic to instead divide the future from the past. Although Heisenberg's quote is much shorter, it seems reasonable to imagine he meant something similar. Of course, just like in Copenhagen, we are allowed to use a classical description of events in the past. We just must be aware that we do not gain any increase in predictive power. For example, we can measure the linear polarization of one of two entangled photons in the EPR setup and the circular polarization of the other. Making use of conservation laws, one can then assign both kinds of polarization to each photon, but because that requires an exchange of classical information, you cannot use the results to send signals faster than light. Realists may use this to argue that quantum mechanics is incomplete. To the extent that we are following Dyson in repositioning the boundary in Copenhagen, we can call this the temporal Copenhagen interpretation, and it looks pretty likely we can make an argument that as far as the practice of quantum mechanics is concerned, temporal Copenhagen is equivalent to Copenhagen. This is good because no experiments are known presently whose results are inconsistent with the Copenhagen formulation. Is our proposal consistent with the other approaches to quantum foundations? We emphasized that our first principle is that the fundamental distinction in nature is between indefinite and definite. Is there an equally basic distinction in the quantum theory that mirrors this distinction? The correspondence is: if a process or observer is indefinite, the amplitudes for the different possibilities are summed over in the path integral before the absolute values squared taken to give probabilities. The amplitudes for definite processes are not summed over. Rather, we form the probability for each definite process by directly taking the absolute value squared. Often this is all you have to do, because there is just one definite history. This correspondence is fundamental to quantum theory, but it cannot be the whole story, because it doesn't dictate when the two rules are applied. When are the amplitudes of the quantum histories summed over and superposed? And when is there a real event where only probabilities are summed? And are these consequences of external interactions, as in von Neumann's two rules for measurements asserts this correspondence is fundamental to quantum theory, but it cannot be the whole story because it doesn't dictate when the two rules are applied. When are the amplitudes of the quantum histories summed over and superposed? And one, is there a real event where only probabilities are summed? And are these consequences of external interactions, as in von Neumann's two rules for measurements asserts? I think I need to put this in two parts. I'll put a little pointer here. Set. Not bad. This is much later from Smolin, and I checked it a little bit yesterday, but my impression yesterday and today is that this is very helpful to understand Unger / Smolin's The Singular Universe. It helps actually. It might seem as an extra conundrum to overcome, but this is an expansion of the previous idea that makes it more sensible. In a way, if you really think of it, mustn't all of the past be present in the present? And oddly enough, I have great help from Julian Barber here. Think of his crystals, those of you who have studied Julian Barber. They contain everything. And although Julian Barber is, as you might recall, more deterministic, take that same idea and put it in Smolin's more flexible, and I would say more connected to proper experience view, the fluidity of the now. And of course, some of you have already noticed this even more brings us to a certain Greek philosopher whose name begins with an H and ends with tus. I will go into that later. I don't want to digress here. It's still a handful to digest, but incredibly interesting. This might be a further help. Thank you very much, and have a pleasant last half hour of the morning. it is almost clearing up. The cold front is doing its job. It is sweeping through Sweden, coming on in from the northeast, and will fix might be a clearer climate. We long miss the sun.